So yeah, I'm going to talk about one of the payloads on Blue Ghost Mission 1. Next slide, please. So Lister is meant to be a heat flow probe. So then to actually determine the heat flow, then you have to make temperature and thermal conductivity measurements at multiple depths. Then also those measurements need to be made deep enough to avoid any influence from the sun. So that's why in the past there have been only 2 successful heat flow measurements on the moon. So those were both done by the Apollo astronauts. So they have never been heat flow measurements on the robotic mission. Then of course when you try to implement, then if you try to, sort of what the Apollo astronauts did was just drill a hole. They had a rotary percussive drill and drill a hole 2.5 meters deep and put the sensors down, right? Then if you try to do that on the robotic mission, then you will soon realize that your mechanism is going to be so heavy and big, and it uses so much power, so it won't fit on the CLIPS lander. So that's why we have to be a little bit creative about how we actually get to the deep enough subsurface. Then we're going to show in the next slide that we ended up doing was to use the technique called the pneumatic excavation. So that's why there have never been any pneumatic drilling on the moon either. So that's why there are a lot of challenges. A lot of the first hurdle we have to kind of go over. Then here's the schematic, actually the photograph of Lister. So that's actually the one flew. Then so this Lister is accommodated below the deck of the lander so that it avoids any heat from the sun, at least a direct heat from the sun. Then also it's for the proximity to the ground, right? Then if you look at the drawings on the left, so that kind of has a see-through kind of X-ray-like drawing. So we have this stainless steel tube, 1/4 inch in diameter, that's spooled inside our deployment mechanism. Then so as that stainless tube spools out, then it gets straightened. Then at the leading end of the stainless steel tube, so we have this nozzle, so that emits pressurized nitrogen gas. Then also at the leading end, we have the sensor in a stainless steel needle. Then so we have 2 RTDs, one in the middle, the spare ones just inside the nozzle. Then we also have a heater wire run through the needle to do the heating experiments to measure thermal conductivity. Right. So as the tube spools out, gets straightened, then hit the ground, then we get the gas going. So that's why we use this momentum of the gas jet and the push from the motor to actually go into the subsurface. Right. Okay. Then so the total weight for this system is 13 kilograms, including the avionics box. Next slide, please. Okay, so this is a picture of Blue Ghost already encapsulated on the payload fairing of Falcon 9. This picture was taken like 2 days before launch. Then you can see, Lister accommodated on the below deck there. Next slide, please. All right, so we're gonna sit on this one for a while. All right, so Blue Ghost landed in the early morning hours of March the 2nd. Then so we started Lister operations about 48 hours later. Then so this is a graph that shows you the progress of how Lister advanced subsurface, right? So if you just follow the blue line, right? So just to show you, okay, so if you try to advance the slide, it should start the video. So we have a below deck camera that was monitoring Lister's activity. Then so as you blow the gas, as you can see, you see the plume of the regolith, right? Then suddenly you see this explosion. So that happens when you drill through a relatively lithified layer. Then you have a bigger explosion there. So that's when we poke through another lithified layer. We estimate it's about 1/2 inch thickness. But anyway, so that was our first drilling, right? So before we drill, actually, we have to stop on the surface just to do the zero depth calibration. So that's why we stopped when the needle just barely touching the surface, then started drilling. So initially we went down 30 centimeters, no problem, right? So then after that, so we always intended to go half meter down in each trial. But of course, there's something hard down there, so that's why it always stops prematurely, right? So that's why we have built into this mechanism called dithering. So when the needle touches something hard, the weight on bit will increase. Then when we detect that, then the lister automatically do this piston-like movement, all right, to kind of move the obstacles aside while we blow the gas. Right. Then if you look at the little sort of graph in the middle, so that shows you how actually, from going down from one depth to the next, actually lister engages in these dithering several times to get going. Right. So that's why, in the end, we advanced, maybe, 10, 20 centimeters at a time, but we find that we always managed to keep going. By this, by pushing and shoving literally, and then do the tethering movement. So that's why by the second day we were able to reach a meter depth. Then we collected measurements at I think 6 or so depth, right? So then that's when we got really stuck. So we ran into something really, really hard. Then if you recall, so the Apollo astronauts drilled 2.5 meters deep, right? So that's the depth we were aiming for. So, so by 1 meter depth, the influence from the sun is very small. So that's why we're just diving into our data to see, okay, if we can actually extract the signal from the heat flow coming out from the interior of the moon. Next slide, please. Yeah. So then I just mentioned that. So we went through multiple layers of lithified regolith. Then so we suspect those are the regolith breccia. So then this image is from one of the STMD payloads called the Scalps. Then you can see the lister's hole on the left side of the image, right? Then so when the lander landed, of course, all these thin, loose layers of regolith kind of got blown away. Then what was left exposed was these semi-lithified, which we think is the regolith breccia. So that's why in reality, we always hope that we're just drilling through like some loose sands or something. But in the reality, we have to actually drill through those number of those layers, even if we can avoid hard rocks. So anyway, next slide, please. All right. So what we are working on now is to actually determine the so-called equilibrium temperature. So the temperature of the regolith that was disturbed. Before that was disturbed to estimate. Then also thermal conductivity. Then to do the thermal conductivity, we heat up the regolith, right? Then see how high the temperature gets. Then, so if the temperature gets very high, that means the regolith is very insulating, and vice versa. Then we try to sort of duplicate that experiment with the finite element modeling to actually determine the heat flow of the regolith at each depth we stopped, right? Then I guess next slide, please. Yeah. So anyway, so that's why, like I said in the beginning, so Lister basically made a lot of firsts. We confirmed that the pneumatic excavation works, right? Then it's also possible to make multiple temperature and thermal measurements to multiple depths that also had never been done before. Then we go to 1 meter depth. Then so we're hoping that we can still get the information about the heat flow. Then also, if you remember from Brad Bailey's talk this morning, so there's already Lister 2 scheduled to fly on the Draper mission. So hopefully we can also make another crack at it. So thank you very much.